Sage Geosystems. Thanks for coming here to listen to Dr. Lev Ring. Bureau has an ongoing collaboration with Sage Geosystems on a field project in Houston and many other projects. So thanks, Lev, for coming here. So I'm going to introduce him today. Dr. Lev Ring is the president of Sage Geosystems, a new geothermal venture that he co-founded. Prior to that, he was director of engineering and R&D at Weatherford. During his tenure at Weatherford, Lev managed drilling and well construction engineering R&D teams. Prior to joining Weatherford, Lev was the co-founder and CTO of Venture Global Technologies, a Shell and Halliburton joint venture. Lev holds more than 100 patents and has received numerous awards, including the 2016 World Oil Innovation Thinker Award. Lev holds a PhD in physics and mathematics and a master's in aerospace engineering. Lev is going to talk about geothermal base load and energy storage in hot, dry rocks, advances and challenges. And the stage is yours.
Thank you very much. Today, I'm going to do a little bit different presentation. Usually, I talk about vision and global scale, about geothermal, how we can quickly implement and expand it. But we are a private company and we need to make money, okay? So, let's see. We're going to discuss different type of geothermal systems, okay? And so we will talk about why enhanced geothermal systems or different types of geothermal systems when you want to harvest heat from hot, dry rock is very difficult. And we will discuss how to move from cost to power and how friction is our biggest enemy. And then I'll talk about our technology, SACE technology, which we call HeatCycle, and how it helps to resolve some of the fundamental challenges. And then we're going to talk about several potential implementation, geothermal as a storage and geothermal as a base load. And then we're going to talk about geothermal storage, its flexibility and economic potential. So everybody knows that geothermal is base load power. And so if we're focusing on mid enthalpy, which is usually defined like 150 C to maybe 250 C, the boundaries can be flexible. But the key is we have drilling technology today, we have well completion technology today, we have all technological building blocks that requires to drill and access this type of technology. And there is expertise and equipment in oil field, and there is expertise and equipment in power generation side. So technology is there. So how we can quickly develop it into commercial applications. There are 4 potential ways to harvest geothermal power. One is conventional, it's hydrothermal, you drill to the hot aquifers, and then you produce water, hot water or steam, and then you convert it to electricity. We're not going to talk about it today. You can potentially do it in sedimentary rock, and everybody knows about Pleasant Bio effort in 90s. The key is and was that the well that was flowing 20,000 barrels of water a day at around 150 C was producing only quarter of a megawatt of geothermal power. And after 40 years, we probably know how to improve it, but improving it will give you half a megawatt. You need 10 times more to be economical. Then there is a so-called closed loop. You pretty much drilled and built downhole heat exchanger. You probably all know Professor Van Oort, Eric Van Oort, who published a lot on this. It can be done. The challenge is rock has very low thermal conductivity, and you need really large surface area of contact, okay? And very large meaning that for like 958 pipe, you need around 20 kilometers or 60,000 feet of contact, okay, to get to like 3 megawatt of electric power. It is probably doable based on today's technology, but it is very expensive. And then there is enhanced geothermal systems, and then there is our approach. We'll talk about it in detail. So, why it's so difficult? Power, money, and then friction that kills it. Okay. So any geothermal system needs to integrate subsurface and surface, okay? And so if you're sitting on the surface and you need to generate power, there are two things you worry about. You worry about mass flow rate, you worry about temperature and pressure, and that's pretty much it. You don't care how this heat is being harvested downhole, okay? So if this power manager sits on the well, he just wants a lot of mass flow rate, okay, at a high temperature, okay? And he tells the guy below, just deliver it to me, okay? But the key is, at the surface, you really don't worry what technology is being used to harvest this heat. Let's look at the money, okay? Some of you probably know what is levelized cost of electricity is, but it is a metric that being used to compare different ways of cost of different electricity produced from different sources. And the way you compare it, you take all the investment over the life along through the life of the project, CapEx, OpEx, cost of the fuel, take net present value, and you normalize it on a total electricity produced. And because it's normalized on a total electricity produced, so you can compare like solar with nuclear or solar with geothermal, because capacity is in your denominator, okay? So it's all normalized. And today, if you go to utility and say, well, I have a base load, you can get between 7 to 8 cents contracts, okay, for many years, okay? So here is a simple example. Geothermal utilization is 90%, life 30 years. You put discount rate of 6%, and you assume that your power plant produces 3 megawatt, and then you get to LCOE at 7 cents, and you assume that your CapEx, total CapEx for this is 21 million, and your CapEx per megawatt is 7 million. By the way, so geothermal doesn't have fuels, so that goes to 0, and OpEx is very low. It's 1 cent per kilowatt hour, and so for all practical purposes, you don't worry about OpEx, okay? What you worry about is CapEx per megawatt. That's where the biggest problem is, okay? Without dramatically reducing it, it's not a good picture. Well, let's now play a different game. So let's say we're in South Texas, okay? And we're drilling for 200 C, okay? And so in South Texas, you expect 200 C between like 15 and 20,000 feet. Okay, good. Okay, so what we're going to say is we want our system to have either LCOE 7 cents per kilowatt hour or 8 cents per kilowatt hour. Well, we'll say that our system would require at least 2 wells. Okay, it doesn't matter what technology we'll have to inject in 1 well and we're going to produce from another well. Okay, we also know that in South Texas, to drill to this depth, it will cost you, actually it will cost you today around $11 million, but you're going to be very generous, okay? And I'll say that I can do it $9 million, okay? And that's all you need to know to say to break even at 7 cents, you need to have power plant that produces 5 megawatt net, okay? So without when you take into account all the losses, everything, you need to produce 5 megawatts, okay? Just to break even, okay? And if you want to lower your return on investment and you can live with 8 cents per kilowatt hour, then your net becomes 4 megawatt. The moment you say this, you can immediately calculate what rate, mass flow rate or volumetric rate you need, okay? And that happens to be 50,000 barrels a day at 200 C reservoir, okay? If your reservoir 150 C, that becomes like, because this depends like more than a square of the temperature. So that becomes like 100,000, okay? And that becomes like 40,000 barrels. That's pretty much answer the question, in Texas, we produce geothermal from geopressured reservoirs. I'm not aware of any reservoirs can sustainably produce these types of flow rates, okay? And that's answer why Pleasant Bayou, okay, at 20,000 barrels per day, were producing only half of megawatt, okay? Because it was not 200 C, it was like 140 C, okay? And that's big problem. So from our perspective, the chances of using aquifers to directly generate geothermal power in Gulf area is very limited if they exist at all. Okay. The moment you say what are flow rates, now you can calculate what tubing do you need, okay? And so here is very simple comparison of 5.5, 7-inch and 9.5/8. And what happens is in 5.5 and actually in 7-inch, just friction in the tubing, okay? I'm not counting what happens in the reservoir. I'm not counting everything else. Just flowing in and out at this depth, friction kills you. Because remember, we were talking about net. The moment you start comparing this, adding this additional losses, now you need more power, now you need larger flow rates, now friction starts building up. And so the minimum tubing, actually casing you need to reservoir level is 9.5/8, okay? Now you can have a line, 7-inch liner down there, okay? And that defines the cost of your drilling and define the cost of completion and pretty much answer the question, can existing oil and gas wells be used to produce geothermal, okay? And the answer is on commercial scale, no, because you will find 3.5, 4.5 tubing, and you just cannot flow, okay, these types of rates. Okay, moving along. So, EGS system. Brilliant idea, drill 2 wells, frack between them, circulate, and produce electricity from hot, dry rock. And 45 years of research, a lot of hundreds of millions of dollars invested, zero generation capacity as of today. There is no way in the world power plant that producing power using this technology. And we'll try to answer, there are 3 main challenges. And unless you address them, you cannot do it commercially. And it was understood earlier on that for 150, 200C, you need, that would match. The funny thing about geothermal, everybody using different unit systems, people doing it mass flow rates in imperial system, in C system, but in volumetric. So you always need to be very careful when you read papers to understand what unit system they're using. But there is consistency. This is kind of the right numbers, okay? That's what you need to circulate, okay? By the way, if you look at all the efforts that were done, successful efforts before, from Fenton Hill to France to Germany to current effort, okay? In Nevada, 10 times less. You can go through the literature and it's surprising. Everybody kind of on a level of 10 times less than what is needed. And that is what is important, flow impedance, okay, or friction through the reservoir, okay? Because before I was talking about only friction losses through the tubing. This is easy to remediate, but then you need to circulate through the reservoir. Okay, well, so again, in 55 and then in 73, all the analytics was done. You can open paper and read how to calculate this. You don't need to run finite element analysis. It can be done on the back of the napkin. And pretty much if you want to lose not more than 10% depletion, thermal decline in 5 years, people like to say 30 years, you don't necessarily need, you can refrac every 5 years. So I'm going to be very generous, okay? You will come up that you need to have a fracture area, surface of your fracture, surface area of around 2 square kilometers. That is a lot. And so you need to have, this is just example, you can, but you need to have 10 fractures of more than kilometer per 1,000 feet long and 500 feet height, okay? To have 10% thermal depletion in 5 years. And now everybody like to write finite element analysis, you build model, you can confirm it, okay? But that takes a lot of effort to do. On the previous slides, it's like 5 minutes exercise on the back of the napkins, results exactly the same, okay? But the interesting thing here is, in all this modeling, people are assuming that fractures are parallel plates, and they're considering flow from parallel plates. That's not how nature works, okay? Fractures are not parallel plates. Fractures have variable aperture, okay? And what happens is, this is not self-regulating system. If you have one fracture with a lower resistance than other fractures, the flow rates will increase through the fracture with a less flow resistance it will cool it down. When it cools, rock shrinks, okay, aperture will increase, and so the flow tends to go. So that's called short circuiting, okay? And if you think about need to arrange 10 fractures, at least 10 fractures, producing for 5 years equally distributed flow, I don't know how to do it. It's super difficult, even to imagine how technically it can be done. But let's assume that we figure it out. So now what is known is we want to achieve impedance not greater than 0.1 megapascal per kilogram per second. Good. Okay. Well, if you look at Fenton Hill, all the results, actual results, it's 10 times more, at least 10 times more than required. But let's assume that we're very generous and we somehow figure out how to do this. And by the way, I was talking about fracture that like kilometer long and 500, but you need to access them through perforations, okay, and exit, okay? So these calculations don't take into account all the flow, all the load, all the impedance, okay, that occurs while you're entering or exiting fractures. But even if you're very generous and you just calculate, okay, flow through 2 parallel plates, and then you can assume that you use propant, okay, at propant, and consider a lot of friction losses, So 20% based on from the net that you assumed, meaning that you need to start increasing flow rate. And again, that immediately results to increasing friction through the reservoir. So what can we do? Let's change our approach. Instead of doing this, let's say we still have 2 wells, and we're going to create fractures unconnected from each well. And then what we're going to do is we're going to pump into this well fracture system, and we'll produce from this fracture system. And then we'll alternate. It's like multi-cylinder engine, okay? In and out, in and out. We went to South Texas, and we acquired Shell exploratory well in Stark County. It was drilled 13 years ago to the depth of around 20,000 feet. It actually had 230 C temperature, bottom hole temperature. It was plug and abandoned. And because it was exploratory well, it had 958 casing up to 11,005, okay? And so at 11,500, the temperature was about, is about 150 C, okay? We didn't open, below it was open hole, it was dry well before, we didn't drill out bridge plug, okay? So there is still open hole below us. And we were able to create a fracture almost 3,000 feet high, okay? And I'll explain how we did it, okay? But we had a packer installed between upper perforations and lower perforations, and we had a real-time downhole sensors inside tubing. It's shifted somehow, but that's supposed to be inside tubing, and that was in the annulus, okay? So we could independently in real time measure pressure and temperature coming into the fracture and coming out of the fracture. So we're able to establish circulation, but what we observed is exactly as in all previous tests. So initially you start increasing flow rate and fluid comes out, but at the flow rate like significantly lower than your design flow rates. And the moment you start increasing your circulation rate, you start losing fluid into your fracture system. And it's actually easy to understand. I'll show it later, but you have a window between fracture opening pressure and fracture propagation pressure. So the moment your friction losses exceed the difference between fracture opening pressure and fracture propagation pressure, you lose your fluid into formation, okay? And so we were playing with this, trying, by the way, it's much easier to circulate in the direction of gravity than against gravity. Against gravity, it just doesn't work very well. We shut in well, and when we reopen it, what happened, all the fluid that we lost came back. Like, wow. So we switched how we operated. We pump in, shut in, flow back. And we tested different flow rates, different time between our cycles. And we had no leak off into formation. It's mudstone at this depth, okay? And actually, because of the heating, while you shut in, your pressure increases. And then you can circulate as many times as we spent 4 months on this well doing this. One thing that we did not expect, because we had real-time sensors, you pump in and you cold fluid, and you expect that when you open, you will have initially cold fluid coming out. That's not how it worked, and we initially couldn't explain it quickly. But then we did simulation, and what happens is when you inject, so you have a huge fracture, and you already put in big pad amount of fluid in it, and now you circulate, you pump in and pump out on incremental volume. And what happens when you inject cold fluid? It has higher density. So in the fracture, it immediately drops to the bottom. And when it drops to the bottom, it expels hot fluid. And so when you open, you immediately see hot fluid at a temperature actually even above temperature that you would expect at the same depth, because fracture was going deeper, okay? And when you expel, and imagine your aperture of the fracture is 2 to 3 millimeters at this, and it has kilometer high and several hundred feet wide, okay? It's huge volume of fluid. It's like you pump fluid between 2 very hot plates, and it heats up almost immediately. And this is critical, that to be successful in this art, you need to be able to, your incremental volume when you pump, your growth in pressure needs not to be more than fracture propagation pressure. Otherwise, you will just start increasing your size of the fracture system. Okay, now, why we are able to grow fractures down? Why do we want to grow fractures down? Well, because temperature gradient is in the direction down. So if you can drill, let's say, to 150 C, and I can frac down 2,000, another 3,000 feet. Okay, now I'm at 180 C. Okay, that's one. Second, as I said, when you frac and you pump fluid, cold fluid drop down. So if fracture goes up, you will have this cold attic, and the fluid, hot fluid, will circulate up and cold fluid circulate down. Well, in fracking business, we know that fractures usually go up. Okay, why? Well, so we use light slurries in fracking business, 11, 12 pounds per gallon, right? And so if you look at your fracture gradient and you look at your head of your fluid, the weakest point is always at the shoe. So if you frac, your fractures will go up and horizontal until it reaches barriers. Okay, so nothing. Now imagine I'll take drilling mud, I'll take heavy slurry, I'll take fluid with 15, 17 pounds per gallon. Okay. Now my gradient is larger than my fracture gradient. So what's going to happen is when you pump from the tubing, it goes up until it intersects, and it will intersect at the bottom, and fracture will grow down. Okay, and actually geology knows this science. Okay, it's called gravity fractures. There are a lot of publications, especially from geophysical community, on how dikes are propagating. Okay, so there is nothing new, just oil and gas, and drilling community knows about this because that's how we lose drilling mud. But usually in fracking community, as I said, they use very light mud, so they don't usually take this. But instead of arguing, what we did, we took a steam plan, which is typical commercial fracking software, and we put 9 pounds per gallon, and you can see that fracture is growing up. And then we put 17 pounds per gallon, and you can see fracture growing down. So even commercial software, okay, does show this effect, okay? And that just, I couldn't put this animation. So that was injecting point with the light, and that was injecting point with the heavy, okay? And we also, as I said, demonstrated in the field. We thought that we are very smart, and we first figured out how to do it pump in and pump out. But later on, we found that in Germany, there was a project for 10 years for geothermal district heating. And they demonstrated, they pretty much use the same technique, and they demonstrated that they can do it on a scale of almost a week. So the idea was on weekends you pump in, and then during week you produce hot fluid to harvest heat. But then Penton Hill published a lot of amazing paper, and they actually also realized this, and they did several tests, but people kind of forgot about it. So it's actually been proven in the field, not only by us, but other people as well. And so to summarize, you can grow fractures down if you have a right density of the fracking fluid. And then the way you operate it, you never allow fractures to close. You don't need proppant. You pump a volume, design a volume of fluid that's significantly larger than the volume of fluid you're going to use to circulate in and out. And this fluid pad keeps formation pressurized and fracture open, okay? Never allowing it to close. And then you operate between fracture propagation pressure and fracture opening pressure and fracture propagation pressure. You cannot get short circuiting in this system, okay? Because your production well and you inject, I mean, you alternate them, they're not connected. There is still thermal depletion, okay? There is no magic. So you need to calculate proper volume of the fracture, several fractures, okay? And so the way we design it, we allow 10% thermal depletion in 5 years. Fractures needs to be at least 200 feet from each other, because over 30 years, the heat front propagates like 30 meters, 90 feet. Okay, so if they are 200 feet from a thermal standpoint, they don't know about each other. And the lower permeability of the formation, the better. We can have certain leak-offs. Pressure builds up. And so as long as the formation pressure are above geostatic, hydrostatic pressure, okay, it's going to come out. And so you build pressure front, and then you can cycle it, okay? But the lower permeability, the better for this. And so here is example. By the way, so that allows immediately 2 types of application: mechanical storage and geothermal storage. So you actually don't need temperature. If you have a fracture system, as I described, and you open and close it, mechanical efficiency of this system is around 70%. So you're deep. So you probably all know that there is a pump storage where people are pumping water up, and then they're producing it. Well, the power is proportional to the pressure. And so if you do it, you can, the larger that is built, the tallest is in Switzerland, it's around 1 kilometer. I can easily drill 5 kilometers in Texas, okay? And footprint is nothing because I store it down, okay? So you put at the surface device which exists, it's called pump as a turbine. So you use the same device to pump in, and then you reverse it. When it produces, you convert it to electricity. And it's supposed to run, but it doesn't. Let's see. Good. Now it does. So we can simulate it, and it shows the injection and production rates, and you have a temperature up and down, and that's how you change your fracture volume by pumping in and pumping out. And so if your temperature is below 150 C, harvesting heat is not economical. You can use this as a mechanical storage with efficiency at about 70%. The moment your temperature becomes above 150 C, now you can store, you can produce, and you use not only mechanical energy pressure, but you also put a binary cycle, you put it through the heat exchanger, and on the other side, you convert it to electricity through the binary system. And now your actual efficiency becomes like 200%. It's not 200% efficiency, it's you start harvesting additional energy from the earth. So it's amazing battery because you use 1 unit of energy to store and you produce 2 units of energy. And if you operate them simultaneously, in and out, that is storage. If you shift them in time, now it becomes base load, okay? It's just multi-cylinder engine, okay? And if you have 2 cylinders, you will have some losses in power because you need to circulate the volume of the cold fluid in the well out. It takes like 10 minutes. But if you have more than 5 wells, more than 4 wells, okay, now it becomes pretty much base load. You can shift it and you can manage this power. If you want, we design approximately 3 megawatt net per well. So, and if you want to generate 50 megawatts, you need around 20 wells. And for each well, you create several fractures. And as I said, you don't design it for 30 years. It's not economical. You design it for 5 years to refract it every 5 years. Okay, and that's how you manage your thermal depletion. That is example, if I want to generate 50 megawatts, then I need 20 wells and I'm going to cycle them in and out. I'll drill it from a single pad. So 10 feet between the wells in one row and 20 feet, and downhole, you need to separate them by like 1,000 feet, okay? And so nothing that we cannot do today, okay? It's not very long horizontals, because if you want 10 fractures, okay, 200 feet, it's only 2,000 feet. And if you assume that you want to refract, okay, it's 4,000 feet, okay? You don't need to be perfectly horizontal. You can do it directionally. And so by the time you operate for 5 years, this section, and then you switch to the next section, and 5 years later, that section will heal because heat continue coming. Economics doesn't work. On a scale of 1, we can build it at 6-8 million per megawatt, okay, capex. And then at scale, we will drop it significantly. And for batteries, you probably know about Inflation Reduction Act, and what it did, it created fantastic tax incentives. And actually, for storage, it allows to stack up investment tax credit with production tax credit. So at the moment, if you're looking at return on investment, battery looks better than baseload geothermal, but not everywhere. I mean, internationally, picture can be very different, okay? And on a above 4-hour storage, you can beat batteries, okay, on a cost basis. I mean, lithium-ion batteries. Okay. Questions?
Hi. Thank you very much for a fantastic presentation. Let's take questions.
Thank you so much. I really enjoyed your presentation. So I have 2 questions, if I may.
Sure.
One is, how did you measure the size and the shape of your fracture? Is it measured or inferred? And then my other question is whether you get any mineralization inside that fracture over time, because 2-3 millimeters of aperture is not very much.
Right. All right. So
Thank you.
for me, it's easier to answer first question. I'll talk about the second one as well, okay? So when we design the volume of the fluid that we need to pump in, so as I said, we designed from 3 megawatt, okay? As sitting at the surface, so I immediately calculate what is my daily flow rate, okay? So I know daily volume that I want to pump in and out. So my pad needs to be 3-4 times more. So first time I will pressurize it by 3-4 times more fluid. Okay, so now I know my volume. Okay, what I don't know, so I can of course run our own software or any commercial software and try to figure out the size of the fracture. But as you guys know, it will depend about geology, stress containment, and 100 other things. By the end of the day, I don't care, okay? Because I want to put this volume, okay? And by cycling, I'll measure temperature and it works, okay? And as long as I can put this volume down and I measure friction pressure when I pump, and I know how to measure fracture opening pressure and fracture propagation pressure. So pretty much I know my window and I know how to manage. It's, if you know what is managed pressure drilling is, it's reverse managed pressure drilling, okay? Now, my control algorithm at the surface, because I want to have a constant power, and depending where I am in my cycle, it's not exactly straight and not exactly linear, but I can have a control algorithm that gives me constant power output over this time range, okay? And because I never close my fractures, I'm in a pretty, it's like air mattress, okay? Pressurized air mattress. Okay, so that's on the first question. On mineralization, it's not area of my technical expertise. It is a problem for all geothermal, conventional or unconventional. So we are talking to different flow assurance experts, but that's the depth of a technical answer. We understand that it is an issue that needs to be addressed. I'm not technical expert, okay? So I don't like, yeah, but absolutely. The only thing we try to keep pressure. So there is a critical pressure and temperature when mineral comes out of solution, okay? So managing surface, we always keep it pressurized. So there is a way of doing this, but still, I mean, we understand it and it needs to be addressed.
So thank you for the presentation. Very nice presentation. So I had two questions to you. So the first one, since you discussed that the killer in EGS or deep closed loop geothermal system is the friction pressure, right? And you know, there is a lot of research going on about using, I'm assuming that you're speaking about water as an injection flow. Is this correct? Yeah, so what is your insight about using the supercritical carbon dioxide
Absolutely.
For like mitigating this problem? So
absolutely.
So this is the first one. The second one, as you know, especially for geothermal system, that 60% of the economics mainly came from the drilling side, right? So my main concern about the SAG method is, if we are going to say it is a base load power, if we are looking for a geothermal base load power, you need to drill a couple of wells, right? Based on your presentation. And of course, this is going to increase the economics of the well a lot, because in EGS system or deep closed loop geothermal system, you're going to drill 1 or 2 wells, right? So I would like to know from you the economics of the SAG system, especially if we are going to design for a base load power.
Okay. So on the first question, using supercritical CO2 as a working fluid to harvest heat. Absolutely. That was how we started, okay? So if you look from a physical standpoint, okay, absolutely brilliant. It has very low dynamic viscosity. I mean, there are a lot of properties I can talk about for another couple of hours, okay? But supercritical CO2 is fantastic fluid altogether to harvest heat. The only challenge is economical. You cannot, I was talking about losing water, and if you lose 5% of water in our system downhole, which you have to assume certain losses, okay? nothing economically, don't care. Well, if you have to buy CO2, then you have to pay at the moment $300 per ton, which kills economics immediately. So the answer to your question, if you are in sequestration business, then absolutely, I want to use this CO2, I'll harvest heat, I'll make money, and then I'll increase pressure and I'll sequester it, okay? But unfortunately, at the moment, there is no supercritical CO2 business, at least where we are. And so we use first water. We patented a lot of around using supercritical CO2. So yes, there is a future for this, absolutely, no question about it. And I have actually at AGU fall meeting, I made a big presentation on actually this technology to use supercritical CO2 as a storage. Okay. Oh, supercritical CO2 as a working fluid to harvest heat and also make money by using it for electrical storage or baseload power generation. Okay. So the second question is, my first part of the presentation, I was trying to address it, okay? So first of all, people are talking about drilling cost. Drilling cost is not that high. I mean, we can poke holes, okay, cheaply. It's well construction cost, right? And completion cost, okay? Because as I said, you have to have 958 casing in it. You have to have 20,000 feet of 958 casing. That's already like $2 million, okay? Then you need to cement, then you need to do this and that. So well construction cost is significant, okay? And yes, it accounts for, in a total economics, 50–60%, okay? Well, as I said, if I have enough flow rate, okay, then the amount of power I generate enough to justify economic. By the way, it doesn't matter what system you use, you still need to pump in or pump out, okay? I can design you single well system where you can do both in a single well. Then you need to have a thermally insulated tubing in it because you need to separate hot fluid from cold fluid. Thermally insulating tubing is super expensive, A, and B, now instead of 958s, I need to drill at least 13 3/8 to depths, okay? So my economics doesn't work this way, okay? So 2 simple wells is cheaper than 1 complicated wells, okay? And then when we start doing it like we do in oil industry, pad drilling, okay, and industrial construction, I'll cut this cost by half, okay? So economics does work. If everything else works, economics does work. Below 5 cents, it's difficult to get to LCOE below 5 cents, but at I mean, in Europe, you are right now above 20 cents. In Asia, you're above 20 cents. Here you are at 8–9 cents. So plus all these tax incentives, if everything else works, it's like between 25 and 30% internal rate of return on a project. Works for us.
So what recovery factor you're speaking about in your business models that you are presenting? So
you have a horizontal section, okay? I have designed that I need 3 fractures, okay? Separated 200 feet, okay? So 3 fractures, 600 feet section, okay? I initially will drill 2,000 feet section, okay? And I'll go to the, I'll go to the bottom of it and create this 3 fracture, okay? And I'll operate them for 5 years, okay? until I have 5%, 10% depletion. Depletion meaning temperature drop, okay? And that's how I design my system, okay? I'll put a bridge plug and I'll refrac. It will take me 3 days of operations. I'll refrac the first section, okay? And now for the next 5 years, I'll do this. And then I'll close my perforations and I'll drill out my shoe and I'll come back. So that's how it works.
I'm mainly asking about how much energy you are assuming in your model as a recovery factor you are going to get from the reservoir. So are you expecting to get the entire energy during production? Because normally when we make a geothermal business model, we assume a very low recovery factor, right? In the literature, recovery factor is from 20 to 40% of the entire thermal energy of the geothermal reservoir. So I'm not sure if you know the recovery factor in your business model.
We don't do it. I don't need to do, I mean, I understand what you are doing, asking, but that's not how we calculate all this, okay? Because you, in a dry rock, I'm just solving heat conduction equation, okay? And yeah, I can recalculate total energy in reservoir and then calculate recovery. It's going to be like in a lower single digits, okay? But that's not my, my depletion comes from the cooling of my fracture systems, okay? So I don't deal with the average, okay? Of course, knowing all these results, I can average over the volume, okay? It will be lower single digits.
Okay, I have a question as well. First of all, Lev, thank you for the collaboration. Just to mention to the group here that we monitor these wells from the seismicity for like more than a year now. Yeah. And we haven't seen any earthquakes, at least for the first year they did the test. Now they're going back again. Right. So we will continue monitoring. I have a question that's more like a geophysical aspect of the system. You open and you close the fracks through this the thing that you suggest, the cycle you suggest. And you say that you do that for 5 years, then you plug, and then you go back again sometime later on. Don't you expect with this system to work out that the cohesion between all those fracks will keep them open slowly so that they don't have the same capacity as they did at the beginning of your process? Okay. So you open, close, eventually. All right.
So when we operate fractures in the normal regime, when you say close, we never close them. So the whole idea is, it's literal. I mean, you can imagine air balloon downhole or air mattress, okay, downhole. I store elastic energy in my reservoir and I operate above fracture opening pressure. So ideally, I'll have some leak off, so I'll have to add fluid, but basically I maintain them open because I can control pressure. Okay, now, when I totally close them, I was in fracking business, okay, and did a lot of refracking, okay. Most probably after when I come back, fracture will not follow original, okay. I don't know for sure. I don't know if anybody knows, but our thinking is as long as temperature regime is restored by thermal conductivity, okay? I really don't care what happened with I'm not circulating through this. I'll put enough pressure. I'll either open it or create new. I don't know, and maybe part of it going to be old and part of it I create new. And it may be not a single fracture, it may be some.
You want to affect your flow model? The temperature will be the same. So we assume the temperature will be the same. We assume.
Right. Okay. Right. So my answer to you, I don't know yet. Okay. Our modeling show that it's manageable. 5 years ago, we'll meet in this room, I'll tell you.
We are close to 10.
Yeah.
So I will just take few questions which are online. So there is a question by Sam Clarin, and he asked, have you all explored using supercritical SCO2, yeah, as the downhole working fluid.
Right.
Could the heat root system be implemented at lower temperatures, shallower depths, if supercritical CO2 is utilized?
Okay, so can it be used? I think I already answered on lower temperature and lower depths, okay? Yes and no. So I was talking about electricity, conversion to electricity, okay? There are plenty of application, especially like in Europe, okay, for direct heat utilization, okay? For direct heat utilization, absolutely. For conversion to electricity, technically you can convert at above 100 C, okay? Technically, but economics doesn't work, okay? Because as I said, the guy who is sitting at the surface, he really doesn't care what a guy is using. He knows enthalpy, okay, and flow rates, okay? And so for CO2, you will have so CO2 has less heat capacity than water, so you need more to pump more CO2. It has less dynamic viscosity, so you can do all this, but by the end of the day, you will have such a massive, you would require such a massive flow rates that just doing it at temperature below 150 C. And when I say 150 C, 140 may work, okay, it's range, but I'm telling you at 100 C, economics doesn't work.
So just to add to that, how about using CO2 in the heat exchange on the surface, but not in the subsurface?
Or for the purpose of this, so we are using supercritical Brighton cycle with CO2 as a working fluid. I could not put all this in a scope of 45 minutes, okay? So I just decided to, this is the whole different kind of presentation, how we convert it, but yes, we're using supercritical, we developed supercritical CO2 turbine with Southwest Research Institute. We're using supercritical CO2 mixtures because to be efficient, you need to be at ambient below 25 C. It's very difficult in Texas to cool with the ambient below 25 C, but you can modify it using different additives. So there is a perfect winter refrigerant based on supercritical CO2 and summer refrigerant, okay? But that is a different discussion.
I will take the last question. Can you discuss the economic assumptions with regard to the cost of the energy required to do the pumping? To get base load, it sounds like you need at least some power 24/7. So you can't assume you buy power only when it is the cheapest and produce it when it is expensive.
Right. So I can, again, I have a very detailed spreadsheets, okay? So we were talking, the power I was showing you on a first, whatever, third slide or fourth slide is net power, okay? So actually to generate 3 megawatt that I was talking about, you need turbine that will generate 5 megawatts, okay? So then the difference, okay, is going to cover all your parasitic loads, okay? So parasitic loads is included in these calculations, okay? I just did not specifically discuss details, but yes, it does cost money, but you can use the same energy or you can use off the grid. I mean, there are different countries, different arrangements, how you do it, okay? But it's already included in the equations.
Okay, we have passed and yeah.
Thank you.
Thank you very much, Dr. King. It was a fantastic presentation and it was too much data and information loaded. We learned a lot. Yeah.
Thank you, guys.
Yeah. See you next week at 10. Thank you. Friday.
Thank you very much.
Yeah. Thanks for inviting.
Yeah.